Hi everyone, and welcome back to week 8 of data analysis in criminal justice. More importantly, the week before spring break. And so I hope you guys are all planning something nice and exciting for next week, that won't involve this. But until then, we're going to get to our next topic, which is sampling distributions. So I mentioned a couple weeks ago that there are basically two different categories of statistics. There are descriptive statistics that describe a sample or population that you can observe. In other words, that you have in front of you, you can see all the data for, and you can calculate different sorts of statistics for it. And these are the type of statistics that we spent most of the first part of the class talking about. The second broad category of statistics are inferential statistics. And inferential statistics use probability samples, which we're going to cover in a moment, to generalize about a population. And what I mean by generalize is that you take a sample from a population and you use it to try to learn something about the population. So you go from a small specific sample and you try to make a more general claim about what's going on in the population. And there are two types of inferential statistics that we're going to talk about in this class. The first one is called confidence intervals, and that gives you sort of a buffer zone around your best guess for what some population value is going to be. Another type of inferential statistic is hypothesis testing, and that's where you're going to come up with an idea about what's going on in the population, and you're going to see how likely it is that that might be true based on your sample. And I'm not going to go into any more detail about these two types of inferential statistics until later on in the course, but I like to set that up here just to let you know that this is where we're going with everything we're going to be learning about today. But to briefly sum up here, inferential statistics are any statistics where you're using a sample to try to learn something about a larger population. So you're looking at the sample that you can see and you're trying to learn something about the population that you can't necessarily see in front of you. Whereas descriptive statistics, on the other hand, you're only describing what it is you actually see in front of you. Inferential statistics are largely based on sampling. And although there are various kinds of samples that you can take, the gold standard of sampling, and the kind that we're going to talk about here, is simple random sampling. And when I say gold standard, I mean this is the kind of sampling that you want to do if you want to do statistical inference really well. And how you handle samples that aren't random samples in inference is sort of a question for your research methods classes and other things you might do. So for this class, we're not really going to go into that. But you should know that simple random samples are the best kind of sample for doing statistical inference. A simple random sample is defined as a sample in which every member of a population has an equal chance of being selected into the sample. So you're choosing members of this population to be in your sample, and we're saying that for a simple random sample, every single member of the population has an equal chance of being selected. No one or no thing has more of a chance of being selected into the sample than any other thing. And there are two steps to selecting any kind of simple random sample. The first is to list out every member of whatever population it is that you're interested in. So as we learned about earlier in the class, a population can really be anything. It's totally defined by you, the researcher, the theory you're working with. So a population could be something like the population of a country, but it could also be something like criminal justice students at Rutgers, if that's what you're interested in. It could also be something like all ducks in the Northern Hemisphere. Right, so your population is just something that you're interested in. And if you want to take a simple random sample, you have to be able to list every member of a population. So for example, if you were interested in criminal justice students at Rutgers, your first step would be to list every criminal justice student who attends Rutgers. Your second step in selecting a simple random sample is to use some sort of random process to select population members from your list. So a random process could be a lot of things, but what matters is that, well, it's totally random. There's nothing systematic about it. There's no way of predicting who or what thing is going to be selected next. So a random process could be something like drawing names out of a hat. It could be something like using a random number generator. The key is that there's no way of predicting what it is you're going to get in each draw into the sample. So examples of simple random samples that exist out there in the world are things like jury selection, where juries are selected based on a random sample of registered voters. So you have a list of all people who have registered to vote, and then some sort of random number generator or program that can randomly select members of that list is used to pick people who will then get a letter and be asked to serve on a jury. The Powerball Lotto is an example of a simple random sample. So that's the one, for those of you who don't watch the Powerball Lotto, where you've got that big thing of balls, also like bingo, right? You've got that big thing of balls, it spins around, and then a ball comes out. And so it's totally random which ball comes out, and you end up with a random sample of balls. Another example of a simple random sample would be picking crayons out of a tiny pot. So what I did a couple weeks ago when we talked about probability. In doing that, there was each different crayon in there. When I stuck my hand in and pulled it out, had an equal chance of being selected, and I had no way of knowing, which one it was going to be when I just had my eyes closed and was sticking my hand in there. So that would be an example of a simple random sample, where all the members of the population are known, and some random process was being used to select population members from that population. And in this class, we're going to assume that any and all samples we work with are simple random samples. Again, in actual research, you'll often have to deal with the fact that you're not working with a simple random sample, but for the purposes of learning about statistics and using samples to generalize about populations, we're just going to assume that we have these really good quality simple random samples in every sample we use. Okay, so why are simple random samples the gold standard? What is so special about them? The answer to this question is that when you do a simple random sample, you get a sample that's representative of the population. And what representative means in this context is that on average, you would expect the sample to resemble the population in all ways. So another way of putting this would be that the characteristics of the sample, or the sample statistics, will tend to resemble the characteristics of the population, which we can also call population parameters. And if you have a representative sample, you assume that it's going to be similar on anything you could measure. So you'd expect any proportions in the sample to resemble the population. So if you took a random sample of criminal justice students and found the proportion of them who had a minor in something other than criminal justice, you'd expect your random sample to have the same proportion or similar proportion of students with minors as there was in the whole population of criminal justice students. You'd expect them to have similar means. So if you took a random sample of criminal justice students, calculated their mean GPA, you would expect their mean GPA to be similar to that in the population. Same thing for standard deviation. If you were to calculate the standard deviation of the GPA, you'd expect it to be similar to that in the population. And the key thing is, no matter what it is you're measuring, you would expect, on average, to have a similar set of measures in your sample as in your population. One important thing to note here, though, is that you would expect them to be similar, but not necessarily the same. And that's because when you're doing anything with a random process, there is random chance involved. And it's always possible that you're going to get some sort of unlikely set of draws when taking your sample, and that your sample is going to be different from the population. But on average, if you were to do it over and over and over again, you would end up with the same values on all your sample statistics as on all the population parameters. So one thing to look out for when you're considering any sort of numbers that you see that are coming from a sample is the fact that not all samples are representative. So simple random samples, gold standard because they're representative. What's the problem with non-representative samples then? Well, while a representative sample is going to give you sample values that are really close to the population values, except if you happen to get unlucky, non-representative samples don't necessarily resemble the population in any particular way. And an example of this is this question, do you favor or oppose the death penalty for persons convicted of murder, that I asked you guys in the class survey at the beginning of the semester. And this question is specifically worded this way because it's also a question that is asked year after year in nationally representative surveys of people in the United States. So let's say we wanted to learn about, support for the death penalty in the United States as a whole. If we were to only look at data from our class sample, it would look like this. 44.2% of you guys said that you favored the death penalty, and 55.8% of you guys said that you opposed the death penalty. And that's in a sample of the 52 people who took the class survey. So you might look at this and say, okay, well, we have a sample, and this tells us that in the United States, a majority of people oppose the death penalty. Only 55.8% of people in the sample, 55.8% of people in the sample oppose the death penalty, so we should assume that overall people tend to oppose the death penalty. The problem with doing this is that a class of criminal justice students is not necessarily representative of the United States as a whole. And in fact, you guys differ on a lot of different measures. So for one, and the most obvious one, is you're more educated than Americans as a whole because you're all in college. You also tend to be younger. Other demographics are going to be different too compared to the United States as a whole. So this means that a lot of your opinions differ too from the United States measured as a whole. And so if we're trying to learn about death penalty attitudes in the United States, looking only at a sample of criminal justice students at Rutgers is not necessarily going to tell us so much. So let's compare these numbers now to numbers from a nationally representative sample of people in the United States. As you can see here, the numbers are totally flipped around. And if you sample people in the United States as a whole, you'll see that a majority of them actually favor the death penalty, and a minority of them oppose the death penalty. So if you were to have tried to learn about death penalty to support in the United States just from this data analysis class, you'd be coming away with a completely wrong conclusion, because you'd be missing out on people who have views and experiences that are not represented by people who are in a criminal justice class at Rutgers. So out there, if you ever see numbers in any sort of news report or anything, take a moment and just think about what the sample is and think about whether it's reasonable to draw the conclusions that are being drawn from that sample. All right, so one theme in everything I've been talking about is that when you take a sample, it's likely to resemble the population on a number of different measures, if it's a simple random sample. But I keep saying that it's likely to resemble it, and not that it's going to exactly resemble it. The reason for this is something called sampling error. And sampling error is a fancy way of saying that because of random chance, if you take a sample from a population, the sample is probably not going to look exactly like the population, just because of random chance, no matter how good your sample is. So even if you have the best simple random sample in the world, you are doing it perfectly, there's a chance that your sample is going to be a bit different from your population, just because you happen to pick some members of the population that differed from what you would have expected in some ways. A useful property of sampling, though, is that larger samples tend to have less sampling error than smaller samples. So the bigger your sample is, the more likely it is that that sample is going to resemble the population in terms of whatever it is you're interested in. And so I want you to think back for a moment and just remember what we talked about a couple weeks ago in sampling, and the idea that if you do a lot of trials in some sort of probability event, chances are the unlikely outcomes are going to sort of even each other out, and you're going to end up with something that looks like the probability distribution that you started with. It's the same idea when you're taking a sample. And the more members of a population you draw, the less likely it is that you're going to just have a lot of really weird population members in your sample, and more likely that any unlikely outcomes are going to be evened out by the more likely outcomes that are going to happen over and over again. So to sum up all of that, larger samples tend to have less sampling error, meaning that the larger your sample is, the more likely it is to look like your population. Again, assuming that you're working with a simple random sample. If you're working with a sample that's not a random sample or not a probability sample at all, it doesn't matter how big your sample is. And you could have the biggest sample in the world and it could still suck if you're not doing simple random sampling. And so just to sort of get back to this idea that we talked about before, if you toss a coin 10 times, you'd expect to get heads 5 times, right? Because it's a 50-50 chance. But it wouldn't be that surprising if you got 6 heads. If you tossed a coin 10,000 times, you'd expect to get 5,000 heads, and you should be surprised if you get 6,000 heads. And so this is the difference between a small sample and a large sample. When you're working with a small sample, so something like 10 coin tosses, to get 6 heads, you only need one coin toss to go a different way than you'd expect. So you'd only need one of your outcomes to be different than what the probability distribution would tell you it should be. But if you're tossing a coin 10,000 times, in order to get the same proportion of heads, so 6 out of 10 or 6,000 out of 10,000, you'd need to have 1,000 different outcomes be different than what you were expecting. And that's a lot of times for something unlikely to happen. So it's really, really, really unlikely to happen. Hopefully this intuitively makes sense. If it doesn't, just take my word for it. Larger samples tend to be more likely to resemble the population, whereas with smaller samples, it's more likely that you're going to get some unlikely events or unlikely outcomes just by chance. So let's talk about why this matters. Well, our goal here is to use samples to learn something about populations. But because of sampling error, or the idea that a sample is just going to differ from a population by chance, no matter how good your sampling procedure is, you can't assume that your sample is going to look exactly like the population that it came from. And instead, a sample gives a best guess. So if you take one sample, you can look at the characteristics of that sample, and you know that, on average, most of the time, it's going to look like the population that it came from. But it's still only a best guess, because you don't actually know about the population that you took the sample from. So now this is going back to the homework for that week. If you were to take a sample of 100 public defender cases, and 36 of them are property offense cases, and let's assume that we want to know about the makeup of public defender cases in general, your best guess would be that 36%, or 36 out of 100, public defender cases involve property crimes. But you can assume that exactly 36% of cases handled by public defenders involve property crimes. And the reason you can't assume that is that there could be some random differences between the sample and the population, and because you're only looking at the sample, you'll never actually know what those differences are. But what we can do is take that sampling error into account when we decide on how accurate our best guess is. And as we go through this class, one of the things that we're going to be doing, and actually a main thing that we're going to be doing when we talk about confidence intervals and also hypothesis testing, is talking about how to take that sampling error into account so that we can make a statement about how accurate our best guess is based on our sample. But again, that's for later. Before we can talk about how to apply this stuff, we have to talk about how it works. So in this part of the lecture, I'm going to give you an example of what happens when you take multiple samples. So we're thinking about the idea that when you take a sample, it tends to resemble the population, but often differs from it a little bit. And when you take a sample to try to do inferential statistics, you only get to see one sample. So you don't actually know what's going on in the population, and you have to make your best guess. So in order to learn about how we use that one sample to make a best guess, we're first going to take a look at what happens when we take a lot of different samples. So what I have here is listed a very important piece of information about all of you, which is the number of letters in your first name as it is listed on the roster. So I counted all of these up. If there's any mistakes, I'm sorry about that. I was doing this during a faculty meeting when I was also pretending to be paying attention, but pretty sure I have the right number for everybody. And what I went through and calculated for the whole class is the mean number of letters in your first name. So counted up the number of letters in everybody's first name, again, as it is listed on the roster. Some of you guys might go by nicknames or different names. But what you get here is a population mean of 6.0 letters. So we're going to treat this class roster as our population. This is our entire list of the population, and we know that the population mean here is 6 letters for students in our class. Now let's see what happens when we take a sample of 5 people. And in order to take this sample, I want to point out I just used a random number generator. I got a different number between 1 and 55 each time, because there's 55 students, and based on each press of the button on the random number generator, I highlighted a name. So this is what came out when I took a sample of 5 students by pressing a random number generator 5 times. We get a sample mean of 5.0 letters. So for the students who are highlighted, if you take the mean number of letters in their name, it's 5 letters. Now, I'd like you to imagine that you're a researcher, and you take a sample, and you really want to know the mean number of letters in the first names of students in their class. But you only have the means to look at 5 people to make your best guess about the average number of letters in people's names. So if you take this sample of 5 students, your best guess is going to be that there's an average of 5 letters in everybody's first name. Is that accurate? Well, it's close-ish, right? It's 5.0, and the true population mean is 6.0. But again, we're only imagining that we can only see this one sample of 5 people, and we have to use that to make our best guess about the population mean. So an issue here, as you can see, is that when you only take one sample, you might be a little bit off. But let's now see what happens when we take a whole bunch of samples. And I want you to pay attention to how close or how far away the sample means are when we take 10 more samples. Sample number 1. And if you guys are wondering, I actually went through and I pressed the random number generator 5 times for each of these slides we're going to go through. Also during this faculty meeting in which I was paying lots of attention. All right, so in our first sample here, we have an average of 6.4 letters in the first name. Second sample, 6.2. Third sample, 6.4. Fourth sample, 6.0. So sample number 4 here, just notice quickly, this gave us the exact mean number of letters in the first name, but it's the only time this has happened so far. All right, 6.4 in sample 5, 7.0 in sample 6, 4.8 in sample 7, 7.4 in sample 8, 7.2 in sample 9, and finally 5.4 in sample 10. So as I went through, you should have noticed that sometimes our average number of letters in the sample was pretty close to 6.0. If you get lucky every once in a while, it'll be the exact average. But most of the time it was pretty close, with a couple of samples that had a particularly high mean number of letters and a couple of samples that had a particularly low number of letters. And what I'm going to do here now is just put all of this on the slide for you to look at the same time. So the actual class mean was 6.0 letters in the first name. When we took our first sample, it was 5 letters. And then our next 10 samples gave us the following means. What you can also see here in this frequency distribution is how these different values are distributed. And what you should notice is that, for the most part, the sample values that we get are clustered around 6.0. And we have some that are further away on either side, but for the most part, they're pretty close. When we take the average of our 10 sample means, though, we get 6.3, which is really pretty close. And it's not exact, right? So we had a couple of samples that had particularly large means. That happens just by random chance. But it's relatively close to what the actual mean is. And the cool thing is that you can do this as many times as you want, and this is always going to be the case, where if you take a whole bunch of sample means, they'll be spread out, they'll be mostly clumped around the mean that you're looking for, but if you take the average of all of them, it's going to give you a value that's pretty close to the true mean in the population. And some years it's closer than others. 6.3 is one of the further ones I've had in terms of being close to 6.0, but it's still pretty close. So if you were to do this, take your average of all your sample means and see that it's 6.3 letters. If you made that your best guess, you'd be pretty close. And what's going on here is that when you take sample means, the most likely thing to happen is that your sample mean is going to be similar to your population mean. So most of the time it's going to be around 6.0. Even if it's not exact, it's most of the time going to be there. Sometimes it's going to be larger and sometimes it's going to be smaller. But for the most part, it's going to clump around that true population mean. And then even cooler, if you take the average of all your different sample means, it gives you an average that is really very close to the population mean. And what all of this goes to show is something that in statistics is called, or falls under the umbrella of probability theory. And so we're going to talk about what this actually means in terms of understanding samples and using samples for inferential statistics as well. Okay, so the takeaways from what we just did on the last slide should be the following things. One is that when you take a sample mean over and over again, you get different values. Another is that those values differ from each other, but they all tend to clump around a particular value. In other words, some sample means are more likely than others. And all of this comes together to hopefully help you understand the following. And what I'm going to talk about specifically is something called a sampling distribution. And specifically, a sampling distribution is a list of all possible values of a sample statistic, such as a sample mean, and the probability of getting each one. So if you were thinking about a sampling distribution for the mean number of letters in names of people in our class, all possible values of the sample statistic would be all of the possible sample means that I could get. So given the people in our class, you could think about the lowest possible sample mean you could get and the highest possible sample mean you could get. And that would totally depend on just the numbers of letters and everybody's names in the class. So you can only get so low and you can only get so high, but you can have anything in between. So the first part of your sampling distribution is all possible values of your sample statistic. So for example, all of the possible mean numbers of letters that we could have gotten in the last exercise. The second component of the sampling distribution is the probability of getting each of those possible sample statistics. So what's the probability of getting different possible sample means? And again, one thing that you should have pulled from the last slide is the idea that some sample means are more likely than others. So sample means that are closer to 6, which is the actual population mean, we saw that those were more likely, while higher ones and lower ones, so anything less than 5, anything more than 7, they were less likely. But you could formally plot all of this out in a sampling distribution, which would tell you those possible values and then the probability of getting each one. So this should be sounding relatively familiar also, because when we talked about probability distributions, we define them as all possible values of a variable and the probability of getting each one. So really the only difference here is that instead of looking at the possible values of some variable, we're looking at the possible values of a sample statistic. And then of course the probability of getting each one. So just like a probability distribution, a sampling distribution can have a lot of different shapes. And we tend to show these in graph form in the same way that we do with probability distributions, such as the normal distribution that we met last week. So example probability distributions would be these here, where you're listing out the possible sample means that you could get. So X bar refers to a sample mean. And then you're showing their probability in this graph form, where higher values are higher on the graph and lower values are lower on the graph. So you can see with each of these, your more likely sample means would be the ones that are higher on the graph, and your less likely sample means would be the ones that are lower on the graph. And so in thinking about what we did on the last slide when we made the graph of the sample means that we got in the class, you should have seen a sort of familiar shape there where our more likely sample means ended up making a higher peak in our graph, and our less likely sample means as we moved out towards the sides were sort of the lower parts of that graph. Those were funny shaped graphs, but for the most part, when we deal with sampling distributions, we're going to be dealing with a specific and also familiarly shaped graph. And in particular, sampling distributions are normally distributed when one of two things is true. Either the underlying variable itself is normally distributed. So if the mean number of letters in everybody's name was normally distributed, so that bell curve, that we met last week, if that was the case, we would expect the sampling distribution for the mean number of letters to be normally distributed also. In general, mean number of letters seems to not be normally distributed because you can only have so short a name, but you can have a pretty long name, so it's a little skewed. But sampling distributions are also normally distributed when the sample size is greater than 30. And this latter one, so the idea that the sampling distribution is normal when the sample size is greater than 30, is true no matter what the variable itself is distributed like. So you could have the most skewed variable in the world, and you're still going to get a normally shaped sampling distribution when the sample size is greater than 30. And this property of sampling is called the central limit theorem. So now we're going to look a little bit more closely at sampling distributions for means. So you can have a sampling distribution for lots of different sample statistics. You could map out, all the possible standard deviations that a variable could have and the probability of getting each one. You could map out proportions and the probability of getting each one. But we're going to focus here on means, which is for the most part what we've been talking about in examples throughout this lecture. So thanks to the central limit theorem, the sampling distribution for means is normal if either the variable itself is normally distributed or the sample size that you're looking at is greater than 30. This means that a sampling distribution for means can be treated like any other normal distribution, and it has similar properties as well. It has the familiar bell shape that you've come to know and love. It has a mean and something called a standard error. So the mean of the normal sampling distribution is given by that little phrase there, mu sub x bar, where you have the letter mu, which we met before and referred to the mean of a probability distribution. Here it refers to the mean of a sampling distribution, and we note that it's a sampling distribution for means by putting that little x bar, which stands for the mean, next to it. The standard deviation of a sampling distribution is referred to as the standard error. So this is essentially the same thing as a standard deviation, it just has a different name when we're talking about sampling distributions. And the standard error for a sampling distribution of means is given by the Greek letter sigma, which we met last week as the standard deviation for a normal distribution. But here we're saying that it's the standard error, aka standard deviation, for a sampling distribution of means by putting that little x bar for mean next to it. As with any other normal probability distribution, a normal sampling distribution can also be used to find the probability of getting an outcome within some range of values. And we do it the exact same way by using the area under the curve to tell us the probability. This means that familiar things like the empirical rule still apply, and you can also calculate z-scores and use the z-table in the exact same way as you would for a normal distribution that's just telling you the probability of getting different values of some particular variable. So again, this is just a little asterisk standard error. When you hear me say it or see me write it, is just going to be the term for a standard deviation in our sampling distribution. So you can also draw out this normal distribution, and it's going to look a lot like the normal distributions that we saw last week. And again, the main difference is that what we have on the x-axis are sample means instead of variable values, and our standard error is going to be written, as this sigma sub x bar as well. You'll also see me referring to the mean of a sampling distribution of means as the overall mean, just to distinguish it from the sample means that we might be talking about. So the overall mean of the sampling distribution of means is this mu sub x bar, and the standard error is sigma sub x bar, and that's the standard deviation for this distribution. So how do you figure out what the mean and standard error are in a sampling distribution of means? Lucky for you guys, it's not too complicated. And specifically, the mean and standard error for your sampling distribution of means are going to be based on the probability distribution for the variable you're working with. So if we were thinking about the numbers of letters in everybody's name, we'd be able to figure out the mean and standard error for our sampling distribution. So again, that told us all the different possible sample means you could get and the probability of getting each one. You'd be able to figure out the mean and standard error for that distribution by looking at the actual distribution of the numbers of letters in everybody's names. The overall mean of your sampling distribution of means, or mu sub x bar, is going to be equal to the population mean. So that one's pretty easy. And this tells us that in the example we had, oh sorry, not in the example we had, because those were small samples. So you'd have to imagine that we were taking much larger samples for that to be true. So I'm going to just cut myself off there. But when we're going to go through examples in the document camera after this, so this will get a little bit more concrete. But for now, I'm going to stop going further in that example because with samples of 5, the central limit theorem does not apply. So the overall mean of your sampling distribution, or mu sub x bar, is going to be equal to the population mean of the variable that you're interested in. So mu sub x bar just equals mu. The standard error for your sampling distribution, or sigma sub x bar, can be found using something called the standard error formula, which I'll show you in just a moment there. One thing to note though before I hop over to the document camera is that when you have larger samples, you're going to have a smaller standard error. So in other words, if your standard error is like your standard deviation, the smaller it is, the more tightly everything is going to be clumped around your mean. And what this reflects is the fact that when you have a larger sample, it's more likely that your sample mean is going to resemble your population mean. So your possible sample means are all clumped really tightly around that population mean. Whereas when you have a smaller sample, it's more spread out, and you have more of a chance of getting sample means that are really high or really low. And otherwise, I'll say it again, once you have a normal sampling distribution, you can use it like a regular normal distribution to find probabilities or use the empirical rule or whatever else you might want to do. So with that, I'm now going to go over to the document camera. This is a lecture with one lecture and one document camera. And I'll go through some examples of first how to find these parameters of your sampling distribution, so the overall mean and the standard error. And then I'll show you how to apply it to find some probabilities and other things we might be interested in.